Okay, good morning, everybody. I hope everyone's having a wonderful day. So today we're going to be talking about a bit about proof of correctness. Then I'll be moving to complexity analysis. And depending how far along we get with that, I might be able to start talking about asymptotics, so-called asymptotic notations. You may have seen these before in a previous course, but I'll be going a little deeper. So just I wanted to remind you of something from last day, because this is going to be quite relevant for what we're going to be doing here in a moment. So I just want to remind you about linear search and how linear search in the way I've described it here works. So first I start with a variable I, and I assign that to 0. And then I have this while loop. And in the while loop, assuming these conditions, these two conditions are both held, I increment I by 1. And then I check after, if I exit out of this loop, that if it's I is equal to n, and otherwise, I just return the position in question. Remember, I'm trying to solve this search problem where I want to know whether x, this element x, you can think of it as a key, is in L or not. So if I know where it is, I want to return that. Otherwise, I'm going to return -1 saying, no, it's not there. So just one important thing I want to point out, and I want to give you generally the game plan that I'm going to give you. This will give you the rationale behind the proofs that we're going to talk about in a moment. So first thing, remember I said to prove that the algorithm is correct, I have to make sure it terminates in finite time and it always produces correct output. So the first thing we're going to do is we're going to prove that the algorithm terminates in finite time. So what does that mean? That means no matter what input I provide this, as long as they're problem instances for my search problem, I'm going to be able to ensure that this will finish in some finite amount of time. So it's an interesting consequence of this. If you know it's going to terminate, you know this algorithm linear search here is going to terminate, there's only two possibilities that could happen. It's either this if statement gets satisfied, the condition of it, and it returns -1, or it returns I. So that means that there's only going to be two possibilities, assuming that the algorithm terminates in finite time, for what can happen. That's going to be very important for our direct proof. We're going to be isolating two cases. Each case is going to be one of these two. Is that clear to everybody? So using these two cases, I'm going to try to say and convince you that the algorithm is going to produce correct output via mathematical proof. To do this, I'm going to use direct means to do so. So I'm going to just observe properties that are of this algorithm. As I mentioned, as algorithms get more complicated or the problems in question get harder to solve, this approach will sometimes be applicable, sometimes not so much, because the arguments you're going to need require you to prove stronger and stronger claims or more difficult things generally. So for something like linear search, a direct approach like this is fine. I'll make a couple of remarks about other ways you can prove linear search is correct after this, okay? So let me just move on over here. So just keep in mind these two cases of linear search. They're very important for how we're going to proceed here. So the first thing I'm going to point out before anything is, remember, I want to make sure it terminates in finite time and it outputs a correct answer every single time. That means it's always going to produce the solution for my instance. So is that clear to everybody? So that's the game plan. I'm going to just try proving these two claims here. These two. And if I could do that, then I could say that the algorithm is indeed correct. So I'm going to first start off with proving that this thing actually terminates in finite time. So I want you to first observe that, like I said, the algorithm starts by setting I to the value 0. And then after each iteration of the while loop, observe that inside this loop over here, it's always going to increment I by 1, right? So that loop has two conditions on it. It's that, of course, I is less than n, or you get a match. It's one or the other, but if any one of those two fails, you know that that while loop is going to exit, right? So assuming, of course, now this is I'm just trying to be a little bit fancy with you, but assume that if the while loop could iterate an infinite number of times, meaning it never terminates, then that would mean I would be able to be unbounded. That means I could keep incrementing I forever and ever and ever, right? But the real observation I want to point out is, remember, we have the first condition on our while loop is I is less than n. So, however, that's not possible as the while loop, it requires that I is less than n, right? So you know for certain that while loop, regardless of what's going to happen, is going to exit when this gets violated, correct? So it's going to end as soon as I is equal to n. Therefore, this algorithm will terminate in finite time. Is that clear to everybody? So all I've done is I've just pointed out something about what the algorithm does. And you'll notice that the termination of this algorithm is entirely dependent on the while loop's conditions. So all I do is I point out, okay, well, what's I's relationship with the while loop? And I tell you, okay, well, it only can go on until I is, it keeps going as long as I is less than n, but eventually it's going to hit n, right? And that's when it exits out of the loop. Okay? So is that okay with everybody? Remember, don't be shy to ask questions about these things, because like I said, I'm trying to introduce the idea. So is that crystal clear to everybody? I haven't pulled a magic trick on you. So for some of you, you'll look at this and say, Dan, all you're doing is just explaining what the algorithm does, right? Now, it might look like that, but really what I'm trying to do is I'm trying to argue to you using a logical argument that this thing is going to terminate in finite time. So just don't confuse the two, but it will look a lot like I'm doing that. You also will notice it's very wordy. That's something you'll have to get used to, is that proofs will consist of words and mathematical expressions. So it isn't just going to be writing like an equation or something. It's going to be words mixed with mathematical expressions, if they're applicable. Why? Because with algorithms, I have to describe what's happening, right? Okay. So that's one way I could prove that this terminates in finite time. This is a direct means to do that. I required some observations, and if you needed to prove these observations more carefully, you could pick up a tool like mathematical induction and do that. But I'll talk more about that towards the end of this. For this class, this would be perfectly fine, and it is typical to do something like this, and that's fine. Why? Because linear search is it's not a complicated algorithm, right? But how about this claim? The one about proving the correct output. I want to make sure I go through this one a little bit more carefully because it's relying on that observation I made. If it terminates in finite time, that means that it's going to return in one of two spots. It's either going to be that I is equal to n, and it returns what? It returns -1. Sorry, I'm getting really excited about this. Or it returns the position I. So there's only those two possibilities, so I'm going to dissect into two possible cases. So I'm going to first address the case when you actually get back a position as opposed to -1. Why? Because that's the easiest part of this proof when you dissect it like this. So I want you to observe that the final line of the algorithm returns value I. Now, this is of course correct if you actually think about it. And I want you to, if you don't have it in front of you, look at the while loop and ask yourself, this had to have occurred if I is less than n, right? Otherwise, it would go right to returning -1, right? But that means that the while loop ended when I is less than n. But what does that imply? Well, we have two conditions on that while loop, right? I is less than n, and that L sub I is not equal to x. That means that L sub I is actually equal to x, meaning it violated the condition of the loop and we exited out, right? So that means that the while loop ended when I was less than n, which implies that it is in fact equal. So like I said, it's all about observing properties of the algorithm. So this one is a rather straightforward one based on the structure and the way I presented the algorithm to you. So is this case clear to everybody? So all I've done is I've looked at the while loop and I said, hey, look. It had to violate the other condition of the while loop. Why? Because I was less than n. That's the only way it returns I, right? Okay? Are we all good with that part? I gotta talk about the other part now. So the other part is when we know it's going to return -1. So I'm going to consider when the algorithm returns -1, I'm going to show you that when it returns -1, it is logically equivalent to me saying that the value x is not in L. So if and only if, just as a reminder, if you see me write something on the left side of the if and only if, it's logically equivalent to what I have on the right side of the if and only if. So when I say the algorithm returns -1, that only can happen when the value x is not in L, and vice versa. Likewise, of course, it means that if algorithm doesn't return -1, that means that the value was in L. So I'm going to start off by assuming that the algorithm returns -1, and I'm just going to describe using logically equivalent statements from that conclusion to get me to the value x is not in L. Is that clear to everybody? So if you wanted to really get your teeth dirty and really just bite into this thing like a big juicy burger, you could go prove one side of this, then the other side of it, because it's an if and only if claim. But for this, fortunately, the observations we can make are very straightforward, and they all have a logically coherent but excellent equivalency between what I say based on properties of the algorithm. So you often will find, so for example, on the assignment, this will be no different there. It's that you'll usually just observe some property that happens with your algorithm, and then you'll just say, hey, look, this is what happens when -1 gets returned, or false gets returned, or things like that. And you'll just see, okay, well, what happens? So each one of these next things I'm going to describe to you happens when -1 is returned. So when the algorithm begins, it sets I to be value 0, correct? And then I is increased by 1 by each iteration of the while loop, right? But what does that mean? If it's going to increase I by 1, what does that imply? It implies that both I is less than n and L sub I is not equal to x. That's when we know we increment I, right? It means that both of these two conditions were true in the while loop, right? So what does that mean? What does that mean? So imagine I'm in an arbitrary iteration of my loop. Suppose I'm in an arbitrary iteration of the loop. What does that mean? If I increment I, that means I haven't found x, right? But what does that mean if I extend this? So what does that mean? Because somebody in the chat mentioned it to me. What does that mean? Hurry before the board tells you the answer. Hurry. Okay. Regardless, let's continue here. So that means that when the algorithm compares a value x with some elements in L, it has to do it each time, right? It goes from left to right from each position. But that means that the algorithm is going to compare x against each value in L, right? That's what the while loop's going to do. But when does the while loop terminate? In this case, when it returns -1. Well, it's when I is equal to n, right? So that means it violated this condition, that I is less than n gets violated, meaning that I is equal to n. But what does that mean? That means that it checked all the values of L, right? But none of them equal x. So what can you conclude? That means that when I return -1, it is indeed the case that x is not in L, because I had to have checked every position in L to terminate and reach -1. Yeah, exactly. Perfect. So you're getting the idea. So that's the end of the proof, believe it or not. So with linear search like this, the way I wrote it here, this is sort of part of the finesse of this, and this is one thing I can describe as a remark, is that sometimes when people present algorithms to you, it isn't necessarily in the way that you would implement it, because it sometimes makes it a little bit harder to prove claims about it. So just as an example here, when you're actually implementing something like linear search, you might actually put an if statement inside your loop right here, and you just try to return right away if you could, if you get a match. But you'll notice here, I just like, oh, well, I'll just kind of have it so that it just kind of boots itself out of here after. But my point stands is that you'll notice that the way I presented the pseudocode to you allowed me to make an easier observation about the properties of this algorithm. But you could have done that so in many other ways. You could have written linear search in several other ways. But I just wanted to hope you get some appreciation for how I presented linear search here for you to make it easier to argue the claims I just did. Sometimes you'll find this is pretty helpful when you're presenting an algorithm for the first time. Are there any questions about that? So is my proof clear to everybody? So notice that all I did is I broke it into cases, because here I had exactly two possibilities that could happen. And then all I did was I just made an observation about what happens with my algorithm. And then I just simply said, okay, well, if that happens, this is what the algorithm does. And then that logically leads this to being this consequence. In this case, it was that X wasn't in L. So you'll find, for example, on assignment 1, depending on how you design your algorithm, you might use a structure like this. You might exhaust into cases like I did here, and you just say what the algorithm does, but you're going to try to use that to connect it to some observation you can make. Now, as an important remark about this as well, so an additional remark, I want to point out one other thing, is that, and this is, I consider this rather important. On Monday, I'll probably post, along with my announcement about assignment 1 coming out, I'll present an alternate version of this correctness proof, where I prove the output is correct using mathematical induction. I want to give you just a general flavor of what I would do with this, just the idea, so that when you take a look at this, it'll be pretty nice. So when I, for example, begin, imagine I have an array like this. When I check the first position of the array, so when I reach that first position, I could check whether the X is there or it isn't there. So if that's the case, if it isn't a match, what I do is I check the next position, right? And if there isn't a match, I check the next one. Well, in mathematical induction, what you would do is you would try to prove to me using the length of the array as what you're performing the induction on. So n, you would start off with an array of length 1 and check if linear search produces correct output. And then for the induction step, what you would do is you would just simply extend. So you'd fix some k. So you'd fix some k greater or equal to 1. And all you would do is you would assume as the induction hypothesis that the first k positions were all checked. Now, there's two possibilities that could happen once you're trying to, because in mathematical induction, what you're trying to do is you're trying to show that if this is in fact produce correct output for the first k positions, that I would like to extend that to one more position in my array. So I would like to make sure that the k plus first position also is checked correctly by linear search. So notice that if I use mathematical induction, I can actually simulate the iterations of my loop, which is a very fascinating idea in its own right, and actually has a natural correspondence to the execution of this algorithm. Now, this is what some people call a loop invariant. So what you would do is you would see what conditions are held every iteration of the loop. And in your mathematical induction, what you do is you take advantage of this fact for the induction hypothesis so that you can say, hey, look, the induction is going to basically perform the first k iterations of the loop. And now I'm just going to check if it's equal or not equal here. But here's the neat fact about this, is if you were checking this position, every other position here would have to be not equal to x, because the loop would have terminated before then, right? So believe it or not, when you do induction, it's actually going to break back into a case that's going to look almost exactly the same as your base step of an induction proof. So there is a way you could prove linear search's correctness using mathematical induction. It's actually quite natural. So that being said, I just want to give you a flavor for what you could do with mathematical induction to prove the correctness of an algorithm as well. I'll give you an example of one of these in the notes on Monday. So hopefully it gives you some idea what you might expect if you tried to use mathematical induction. It's also worth noting, I mentioned this concept of a loop invariant. There is also a version of proof of correctness using mathematical induction that's called a loop invariant, where essentially it's a structured mathematical proof that tells you, okay, before the loop, this is what it looks like, this is what happens in the loop, and then when it terminates, it has this portion here. But I'll focus on mathematical induction mostly in this class and some other proof techniques. But I feel like I need to acknowledge that because I want to show you multiple different ways if possible. Throughout this course, you'll get to see plenty of examples of different ways you could prove the correctness of an algorithm. So hopefully that's clear to everybody. I just want to give you a flavor of things so that when you see, say for example, a mathematical induction proof for the correct output part of this proof, you'll get the general gist of this. Okay, so it seems like the chat's doing pretty good. Is everybody good? So I just wanted to give you a flavor for that before we start talking about complexity analysis. So I'm not expecting you to be like pros about all this, but this should be clear to everybody. So you'll see more about this mathematical induction example in the notes. I just want to expose you to it. I won't require you to do it on the assignment, for example, but you will eventually start seeing these types of proofs pop up in this class at some point. But if you want to use it on the assignment, be my guest. I'd in fact encourage it if it makes sense for the algorithm you present on the assignment. Okay? So sometimes, like I said, when you prove a mathematical claim, it's really unclear how you're going to approach it. It depends on the problem itself and what your algorithm looks like. So for example, for an algorithm like linear search, a direct approach works perfectly fine because the linear search is nice and simple. Some other ones, you might take a direct approach, but it requires a lot of mathematical machinery to really get you to where you want to prove the claim you want. Just about lost my turtle. Okay, so we're going to switch gears because we talked about correctness. Now, that's one aspect of analyzing algorithms. Instead, now I want to turn my attention to efficiency. So this is something you may have seen some of in CS 210. But let me just watch you through and walk us through this fun here. So I'm going to talk about complexity analysis next. Okay, so I have a question for you. What are some desirable characteristics of an algorithm? So what are some desirable characteristics of an algorithm? Please let me know what you think. What are some things that you would like if I told you, hey, look, I have two algorithms. I want to know one is better than the other in this way. What ways would you find it? So I see some already. So for example, it works. I like that one from the chat. I like it, that it works. That's usually a very nice standard to have. So in this class, this will be a minimum bar for us. So we'll make sure that the algorithm actually works. So anything I present you in this class, it has to work. So it has to be efficient. So it's nice that it's efficient. But can somebody drill down a little bit for me? So I see, okay, low time complexity, low space complexity. So we care about the efficiency in terms of that it's running time. We care about that, right? And we also care about space usage. So we definitely care about those things, right? It's easy to understand. That's an excellent one. Conceptual simplicity is a very nice one to have. Sometimes algorithm researchers will sit around and say you're working a given area, and the best known algorithm is a really, really nasty looking thing. It's really hard for even other researchers to understand. Sometimes even people like me will sit around looking at like how can I design a much simpler algorithm, whether it be to implement, whether it be to understand it. And this also comes down to another remark somebody made in the chat, is also how to prove it, right? So these are all things that algorithm researchers or algorithm designers would find very fascinating, and something that would be quite nice. If you could come up with, say, an algorithm that has either even the better or the best known time complexity, and it's much simpler than the super technical version of it, the simpler one might be more advantageous because, one, it's maybe easier to implement, easier to understand, translate, and tell people how it works. But generally, the idea is really built around this idea that we want to try to keep things simple if we can. That's a nice trait of an algorithm, but sometimes it's not really, really important because sometimes the problem's very difficult. But it depends. A lot of these you'll find it depends, except for, I think this one's probably the most important one, at least for us in this class, beyond the correctness, that it works. Can be implemented in many languages. I'll do you one better. That it's about its difficulty to implement and its ability to be modified, or what is so-called augmented. It's supposed to be a U, it's sort of melted there. So, for example, if you know that this algorithm relies on some very technical specification, and maybe in some programming languages that's easier to implement than another one, that could be another feature. Another one, and this is one that often gets understated, is that you may have an algorithm that, say, solves a given problem, but it may actually have a feature about it that's very easy to modify to do other tasks. So, for example, you want to solve a different problem. Like that's a feature that's really nice about some algorithms. This is quite common, especially when you talk about data structures. So these are actually really good lists. I think we hit everything I have on my list. So the point here is that I think these are generally some desirable traits. There may be other ones out there, but what we're going to focus on in this class, we're going to focus on, obviously we care about all of them, but at this point we're going to care about this one because we talked already about it works. That's an important part of this. We're going to talk about if it's efficient. So I'm going to talk about complexity. So you might ask, Dan, what the heck is complexity? It's just simply the amount of computer resources an algorithm uses. I'm keeping it nice and simple for everybody because I think this is rather intuitive. So we're going to be concerned at this point about complexity. So you may know of a couple of different common ways of measuring complexity. So two of them, and these are the ones that we'll be interested in, are time complexity and space complexity. So these are the two that we're going to be interested in, is time and space. So time is the amount of time required to execute the algorithm. So when I say that, I mean it mostly in the sense that how long at most it could take. When it comes to space complexity, I'm going to use this term to talk more about, I'm going to be mostly concerned about extra space used. So I'm going to be mostly concerned about this aspect of space complexity. Because if it's some traditional definitions of space complexity will also include the input itself, we're going to be primarily interested in how much memory or space gets used by the algorithm upon being given the input. So hopefully this distinction is helpful for everybody. The main reason why we might use this understanding of space complexity is, so for example, if I give you, say, a sorting algorithm, and it does everything so-called in place. That means that it only permutes elements within the array. It doesn't actually require you to do anything else beyond that. In cases like this, I don't use any extra space. I'm just given the array and I do all the modifications with respect to the array plus some constant space for some variables. So I would say that that algorithm consumes a constant amount of space. In contrast, if I wanted to have, say, a sorting algorithm that creates copies of arrays, you'll notice in this distinction, I'm no longer using a constant amount of memory because I have to create more arrays. And if each one of those arrays is, say, length n, I'm using a linear amount of space, not just a constant amount of space anymore. But if you included the input as a part of this, you would not be able to tell the difference between those two scenarios. That's why this notion of extra space or auxiliary space is useful. Is that clear to everybody? So I'll be mostly focusing on this extra space concept, as opposed to including the input as a part of things. Are we all good with this? I just don't want to be shy. Don't be shy, because... Okay, so let's shift gears. And now I'm going to define a couple of things, because we're going to use these throughout the class. And I should be able to go boom, boom, boom with this, because some of these things you will have seen in 210. But I'll just kind of pin things down carefully for you. So just keep linear search in the back of your mind, because I'm going to use that as the example when I talk about a lot of these things. So first, I'm going to define something called a complexity function. You may know this as a growth function. That's another name for this. I'm just about to write with the cap on, okay? That was pretty exciting. Okay. So a complexity or growth function. So have you ever heard of what a growth function is? I'll sometimes call it a complexity function, so just keep that in mind. Okay, so I'm going to define a complexity function for you. So it's a function f on the size of the input n, which we will write as f of n as an abbreviation. Now, I have a question for you, especially those that have taken a little bit more mathy courses. Why do I say that I'm just going to use that as an abbreviation? Is that technically an abuse of notation? Is it yes or no? It's an abuse of notation. Can somebody tell me why? What is this? What is this? What's f of n? Yeah, it is a function, but there's two parts to a function, right? Like, so I told you that so what's f? F is the name of the function, right? But what's f of n? It's a function of n, but the thing is that this is also, you could also write this down as the output of f given n. So exactly, it's the value of f given n. So that's why I'm saying that we're going to use it as an abbreviation, but it is, in fact, technically an abuse of notation. We're using it as an abbreviation to write that it's f with parameter n. Is that clear to everybody? So the function's called f, but we're going to use this abbreviation sometimes, so don't let it confuse you. So some context, this will mean the output of the function. given n. Other times it'll just be me saying, hey, look, this is the function, its parameter is n. Okay. So we will assume functions on the domain of positive integers. Sometimes it will fudge it and will allow 0. But generally, this is going to be the case. Positive integers to non-negative real numbers. So in technical language, what I'm saying is f is a function that takes as input a positive integer. I use a plus usually to indicate that it's positive. So the z here, blackboard z, that means integer. The plus means make it positive. So as input, it takes a positive integer. And of course, as given that, it outputs a non-negative real number. So I'll just use a little subscript here, just saying greater or equal to 0. Now, if I wanted to be very pure about this, technically, if I care about any program that contains at least one instruction, this will always be actually a positive real number. But for the sake of allowing me to have functions that'll have value 0 in them, I'm going to allow this to be non-negative. So you might see why I might do this a little bit later on. But if you actually were analyzing an algorithm, there's no way that this could be 0. So when I'm talking about these functions, we're going to be measuring the complexity of our algorithms, and we're going to be counting up the number of operations that occur. The only program that could ever spit out a 0 at you would be, of course, a program with no instructions, right? Meaning it has no operations. It's an empty program. Kind of a wacky idea if you think about it, but it's interesting, right? But I'm just going to assume that we're never going to have an empty program. Is that good with everybody? But this notation will allow me to talk about things like log n and allow log to be 0. So that's what a complexity function is for us. So the big idea is that we're going to use different types of analyses to generate or derive complexity functions. And when we do that, we can determine the asymptotic behavior or the behavior of that algorithm's running time with respect to that case for all possible implementations of the algorithm, which is kind of wild if you think about it that way. So to determine the complexity function, we can consider 3 different analyses. That's supposed to say analyses. It's a Friday, okay? We're having a good time. That's supposed to say analyses. It doesn't look like it though. It's kind of it's had a long week. Okay. So let's talk about different case-based analysis. Now, you've probably seen this before in 210. Could somebody tell me what would be a case that would consider that would be like, because there's going to be 3 main case types of analyses we're going to consider. There's going to be so-called best case analysis, average case analysis, and worst case analysis. We'll add to more types of analyses later in this class, but I'm going to start off with those 3. So let's start off with best case analysis. So let's look at best case analysis. So in this case, we're looking for the best case scenario. The best case scenario. So we will identify best, as in quotation marks, I'll describe what that means in a moment, best problem instances. Instance is, it could be a singular one or it could be multiple ones. The main point is that you're going to be so you remember the picture I drew at the first lecture with the picture with I had the problem and I had all those dots for the problem instances. When we do our analysis for this case-based approach is we're going to identify dots with respect to the input size that behave differently depending on which case we're analyzing over. So for best case analysis, we're looking for when the algorithm performs with respect to the input the best case scenario. So this is where we do the least amount of work with our algorithms. It performs the least number of operations given input size n. So if I gave you something such as linear search, so can somebody tell me what's the best case situation with linear search? So what's the best case scenario? Well, that's the time complexity I'm looking for. Yeah, I see it in the chat. It's right when the element is right in the first spot of the array. So when I ask for those instances, so in the best case, so in linear search, the best case instances are those where x is the first element in L. So how many comparisons am I required to do when I do this? I just do one, right? So it requires one comparison. So notice I'm not talking about big O or anything yet. I'm just talking about the analysis itself. I'm trying to identify those instances. So notice I'm not talking about big O or anything yet. I haven't even done that yet. So all we're doing is we have these different cases, and I'm going to take the problem instances, and I'm going to identify cases for where the algorithm behaves in certain ways. Some algorithms will behave the exact same regardless. All the time with respect to the input size. So it'll just be like, for example, an algorithm that has no branching in it, for example, might be one of these. But in many algorithms, the behavior fluctuates quite a bit when it comes to different instances. If I give you two instances and I look at their size, they may differ. That's why we use case-based analysis to help us identify certain kinds of behaviors the algorithm could have and take on. So that's best case analysis. That one personally is not the most interesting because, of course, it doesn't tell you how long the algorithm's going to run, right? It just tells you how soon it could run. So sometimes that's a feature that you would like to consider. But for this class, we're not going to focus so much on that because, well, we want to know how long the algorithm in total takes to run. So I want to know how much time that requires. So we'll have enough time to talk about average case analysis next. So let's do that. Okay, so let's talk about average case analysis. So average case analysis. So an average case analysis, you can think of this as on average. That's the first thing you got to think about. It's on average. And this requires a bit of statistics. So I'll be talking a little bit about some statistics before I proceed. So the idea, of course, is to compute. I will say compute compute, let's say, let's go over, let's go with compute the average number of steps or operations performed over all possible instances over a given probability distribution. Probability distribution. So what will happen in this type of analysis is you will assume a given type of probability distribution, and then you'll perform the analysis over those instances. So it's very often that we'll assume that this is uniform. It's oftentimes a uniform distribution. So it means that every one of the scenarios, given the fixed set of instances I want to consider, it will be uniform in likelihood. So I'm just going to write down a definition, and then probably next time we'll actually go through a full example here, because we'll be spending more time with worst case analysis, which we'll talk more about next time. So I want to talk about expected value. First, has anybody never heard of expected value before? You might know this, sometimes it's called an average, but it's expected value. It's over a random variable. But don't worry, I'm not going to be going too crazy with this. I just want to give you the definition of expected value. Okay, so let me proceed then. So I'm just going to define it quickly for you. So I'm going to say let x be a discrete random variable. A discrete random variable with finite outcomes, x1, x2, all the way up to xn, like this, which occur with probabilities p1, p2, pn, like this. Then the expectation of x, denoted with a really fun E, with an x with square brackets like this, is of course the sum of pi xi, where I starts at 1 up to n, like this. So that's what the definition is of expected value. Now, seeing as we're out of time today, next time I'll walk you through quickly this example here with linear search. I'll put it in the notes, so if you just want to read it in advance, you feel free. I'll go a little quicker over it, so we can actually start getting into the meat and potatoes of doing analysis in the worst case. But I think that's actually a perfect place for me to stop. But I will stress one thing. This is just a big warning here. When it comes to this, you can't assume that so this is the fun thing about probability, is that you can't really just assume that every instance will take on the expected value. It's just because it's an average, right? So there's going to be ones that aren't going to take on the value of the expected value. So we'll use expected value probably in a couple ways in this class. So that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later. Have a good weekend.